happens every semester, every time I teach anything stochastic. 25% of you think, this is nonsense, I'll wait until the real stuff, okay? And so, 25% of you completely failed the quiz, And the thing is that it's like there's 10 definitions. Get some flashcards. You buy 5 flashcards and have 2 definitions per flashcard. I mean, omega is a set of symbols, F is the domain of P, P takes sets and maps them to numbers. All right, there's 2 definitions. And a random variable is something such that you can define the probability that a random variable is less than R for any R. All right, for that to be true, you need to have that this is a member of F. Now, 25% of you don't know that. 25% of you don't know those 3 definitions. I mean, there's only 10 definitions, abstract definitions maybe. I'm not going to write them down. That's your responsibility. But I don't understand. I just don't get it. I think you see those symbols and you get scared. Don't be such a wuss. It's just not that big a deal. I've got a set of symbols, and these are sets. Collection of subsets of these guys. And you need to do that because you've got to define the domain of the probability. What can we define the probability of? And then we need random variables for obvious reasons. And if you don't know this by the midterm, you will fail. I mean, fail. I don't, no sympathy. All right, so get to work. Yes.
Is there any chance we can come by your office and look at it?
I've got the quiz here. Yeah, I'll pass it out after lecture. Okay. Oh, and yeah, we can discuss. Sure. Sure. And I'm not going to make solutions. No way. If you can't make solutions yourself, you come see me. Okay. There's no way. It was not meant to be hard. It was a bit worse than I've seen in previous semesters. I think it's because actually the last problem was a little trickier than I've had before. All right, so enough of that. Enough of scolding. So we launched into this. I'm really glad we did. So a lot of times we have a lot of data. We want to compute not just a conditional mean, but a conditional variance and other things. And a computational trick is to replace to whiten the data. Okay, so this is the innovations. So we take our data and we replace it by these innovations, which is yn minus the conditional mean given the past. And that becomes an uncorrelated sequence. And one thing I didn't mention is that this step might look complicated, but it itself, when you look at the innovations, you can, instead of taking the conditional, wide sense expectation given the y's, you can do it with respect to the innovations. It's the same thing. And the computation of this is much simpler, again, because the covariance of, I'll write it as in. That's the notation I used last time. It's a diagonal matrix. Because these entries are uncorrelated, so you just get a diagonal matrix. All right. So for example, so in, I'll write it one more time. So remember my way of thinking about this. I say it's a covariance of yn comma using this formula. Yep, there it is. All right. So remember the way to think about doing this. You have a covariance inverse to condition the data, and then you go and you multiply a mapping from in to yn. That's how you sort of memorize this formula. All right, cool. And so because of the fact that's diagonal, that inverse is trivial. Yep,
Is there an n minus 1?
probably. Where is it? Yep. And there's so many damn things to say, I could go nuts saying them all. So what I want to do is just blow off the common filter today. But there's a few more additional things to say before this. I don't know how far I'll get, but I'm going to try to, maybe we'll do the whole common filter today in 40 minutes, or maybe we won't. Let's see. Let's see. So, yeah. Okay, so there's a lot of ways to say this. So, I'm going to write this down again as well. So we wrote this down before. So I'll just write it down again. So the same sort of thing is here. And this is the same sort of thing, right? So the conditional mean of this is the mean plus this, and the innovations is designed to be zero mean. So we know what this constant term is. But the magic is it turns out to be, if you look at each, the fact that this is diagonal, you can check that this is actually equal to the mean of x plus the sum from 1 to n. Plus it's the sum of the conditional, the white sense. Put hats here. Yeah, the white sense conditional means. So it's sort of, you just sum up the conditional means. That's the beauty of innovations. You just take each conditional mean and sum them up. So it's the same thing. Basically, this formula, the same thing. Good? Because of the fact that this is diagonal, everything separates. More generally, it's not really more generally, it's just I want to be able to write things in a different way. We might have a couple of random vectors. All right. So let's assume that if I write Z and W are orthogonal, usually that's in L2. It just means that the dot product is 0. But more generally, if they're vectors, I'll just say that the correlation is 0. Okay. And I'll assume things are zero mean here as well, just to make things simple. What happens when how do I update my information then? Well, I'm going to have the same formula. Basically, you can go through the exact same arguments, and you'll find that yeah, this formula still holds. Oh, there's a mistake there, everybody. You know why? Where's the mistake?
-1.
No. No, why is that? No. This is, I'm taking the mean up to n. There's a big mistake there. It's really easy to make. And you'll all make this mistake once or twice. What if x was constant? What if x was a random variable that just took on the value 5? All right, well, the mean would just be 5. And this would be 5. And this would be 5n times. So I get n plus 1 times 5. So the mistake is I forgot to subtract off the mean. It's so easy to do that. Okay, it's very, very easy to do that. So it's actually related to the discussion we had during office hours on Tuesday. Sometimes you can just ignore this and sometimes you can't. Okay, cool. So yeah, here it would be, I'll just use an x bar here. Well, no, well. Okay, so this is true by the orthogonality principle. Okay, just check to see that that you really do. This is x. This is the span of v and w. Or I mean, z and w. So z is a vector, w is a vector. So I'm looking at, this is say if that's 5-dimensional and that's 5-dimensional, this is a 10-dimensional space, or maybe adding constants, so it's 11-dimensional space, a function space. Okay, and basically the fact that w and z are orthogonal allows you to do this decomposition. Just check that the orthogonality conditions hold. The error. So this is what you have to check. This is a statement I'm making. You'd have to check it. You check the orthogonality condition. So when I take the error, take the right-hand side, and I dot it with any zi, do I get 0? And yes, of course I do, because this guy here, for this case, this guy here, the error is already orthogonal to the orthogonal condition holds for this, the orthogonal condition holds for this because z and w are uncorrelated. All right, that's the reason. Okay, now the other thing that's important is what happens to the error as you get more and more information. So I'm going to be thinking of n as time over here, and I want to know, as I gather more and more information, the estimate of the covariance of my error should get smaller and smaller. So how to think about that? All right, so so this is my error given all the data now. I've seen z, I've seen w, and I've got my estimate, x is reality. And I'd like to somehow figure out how the covariance decreases as I get more and more information. It's the covariance of this error. And so the trick is to write things in the right way. I've got that error is just x minus all of that. I don't have to keep writing down that all the time, so I'll just give that a squiggle. That's it. X tilde z is just the expectation of x tilde given z and so forth. All right?
Are you assuming anything about the subspaces spanned by the Z and W?
This is all I'm assuming. I've got these two random zero mean vectors. Their correlation is 0, and that's it. And so this follows exactly from checking these orthogonality conditions. So why you asked that question? Is it about this? Now this is a definition. I'm taking x minus this, and I'm plugging in what.
Just with the, I guess it was about that notation.
I just don't want to have to keep writing this. No, come on. I'm going to have to.
Standard.
Sure. I mean, no, nothing standard. Notation is for simplicity when you're doing something. Whenever you have to write down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 symbols, you think, shit, I can just do it 3 symbols. And if you're really clever, you can do it just 2 symbols. Okay. No, it's just a matter of, I have to write down a lot of stuff. I don't want to have to keep writing this business. Okay, so how am I going to think about this? Well, I know I've got all these orthogonality properties, I know that this guy's orthogonal to all the z's, because this guy's a linear combination of the w's and constants. Z is zero mean. Same thing this guy's orthogonal to all the w guys. And the error, what kind of orthogonality properties does that have? This big guy here? All right. It's orthogonal to everything you've seen. All right. So if you flip this around, you get that, what I called x tilde last lecture. It's equal to the sum of 3 orthogonal guys. Okay. So again, this is the error. By the orthogonality principle, this is orthogonal to any element of z and any element of w. That's the characterization of the optimal linear estimator. Okay, and these two guys are orthogonal again because w and z are assumed to be orthogonal. So they're mutually orthogonal. So when you take the covariance, you'll get the sum of the covariances. And that's a really nice result. But so this is what you get by orthogonality from here to here, and this is what you get by algebra, just by taking these two terms on the other side, and then you do a bit of pattern recognition, and you see, okay, you do a bit of pattern recognition, you see that this must be the covariance from what if I only had the one observation W. So we're seeing it. So the error, the E sub W means it's the error given W, the data W. Right? Same, just omitting the Z, just if I only saw W. So yeah, so it's you get this. I mean, most of you have seen this, maybe. I don't know. It should be a noise. If it wasn't, then somebody should have been scolded. But there you have it. So that's it. So basically, with these formulas, being able to write these sort of kind of recursive formulas for these wide sense means, we can derive the Kalman filter extremely quickly, if only for the fact that we make mistakes all the time. And so it's really hard to do it efficiently. this is a part of the course where I wish I could just bring out PowerPoint, because the symbols and all that are so awful. All right. So is this true? Anybody? Just having fun. Yeah, right? Looks good to me. So you can write lots of things down and then wonder if they're true or not. So, I just, here was the same thing. I was, we'll be using x bar for means. So if you believe this equation, then you can believe that that whole thing is just the mean of x given w. And then w0 mean. And this I just wrote down again. But so given these two things, we can derive the common filter. So I was using Bruce Hayek's notes for the lecture today, not his book, but his July, just before he published it. And I'm sorry, Bruce, but your section is just completely a mess. There's a mistake. I want you all to go through that section carefully in the common filter, and I'll give a prize to whoever finds the most errors. There are so many typos, and it's just that none of us want to do this. The concepts are so beautiful, but the details are so ugly. So I feel I'll walk you through it, okay? So we've got 20 minutes. Let's walk through it. So, what's my motivation? Why am I going to talk about the common filter? It's, anyone can go on Wikipedia and look up the equations and run the common filter. You don't need to know anything to do it. But it illustrates, it's such good practice for all these methods. So it's really useful for that reason. Otherwise, I wouldn't cover it. If it wasn't good for practicing these ideas, I would just skip it. And sometimes I do that. I've taught this course and just said, I give up. Read it on your own. But this semester, we're going to do it. So in the common filter, here's the goal. All right, yeah. Okay, so I've got a state equation and observation. And for the uninitiated, you've really got to think carefully about what we're doing here. So x is the state of my airplane, say. It's, I've got to know its pitch and speed and I don't know what all these things are called. I've got to know the position of all the flaps and ailerons and whatever they're called. There'll be just, this is going to be some 10,000 dimensional object, I think. I don't know. And then I've got measurements, which are this, there's a few measurements I've got, a handful of measurements. And I'd like to, which are given here by y, right? And so based on y, I'd like to be able to estimate the amount that the fuselage is twisted. It's not completely stiff. I'd like to know the angle at which the tail and the wings are twisted relative to each other. I don't have a sensor for that. I'd like to estimate it. I'm just making this up as I go along. So airplanes aren't linear, so you cook up an approximate model. Actually, they do introduce nonlinearities too here, but forget that. But you come up with a model, and you assume you know, and you're really measuring this. I mean, these are observations. You're measuring y. That's a sequence you're measuring. You assume you know the model. So you know h, you know f. You don't know the noise here. That's called measurement noise, and that's called a disturbance. But you assume you know the statistics. And so basically, you know, all the matrices are known. And all the statistics you can think of are known. And what are those? So basically, WK, VK, X0 Okay, so I don't know X0 even, but I know that it's uncorrelated with all of the measurement noise and the disturbance to the system. All right, and the W's are wide sense white, so the W sequence is uncorrelated. The V sequence is assumed to be uncorrelated. And so basically, if that's not true, you've got to somehow change your model. You basically, if these guys you had some sort of correlation, you would increase the state, basically. You would add on additional noise states to model the noise. You know, if the observation noise is not white, you would somehow whiten it. You'd put your observations through some sort of filter to make it look more like a white noise model. Okay, so there's a lot of conditioning and modeling and all this stuff that goes in. And there's some notation, I guess. We let RK be equal to the covariance. Oh yeah, I should. This is maybe the weirdest thing. You assume you know the mean of the initial state. Why would you know that? Luckily, these filters are stable. So if you don't know the initial distribution, it doesn't matter. You'll still recover from that mistake. All right. And then we have some notation. It matters.
If it's controllable.
We're trying to compute this stuff. No, nothing. No, that's a bunch of nonsense. We have one goal. It's to compute it, but there's no control here. Our goal. We haven't said the goal yet. Our goal is to obtain that possibly for every t and s. If t is huge, there's a prediction problem. We're trying to estimate, where I'm going to be far from now. If t is equal to s or s plus 1, that's what's called filtering. And if otherwise, it's smoothing. It's funny language, isn't it? But that's the language. And so you can imagine, t could be 0. And basically that's the situation we were in last lecture. And if t were just 0, that's a smoothing property. We just collect more and more information. We'd like to know the initial guy. We know what we'd do is we would create the innovations process, and we've got a formula, so we're done. So the smoothing property, we've sort of done that in a way. But we want to come with a recursive formula for this. So we're going to stick to just one case. Oh yeah, I forgot, this is notation. I forgot. So we're calling this x hat t given s. And we're going to stick to the filtering problem, which is usually the most interesting to control people. So just the estimate at time t of the state one step in the future, or the estimate time t of the state now. And let's write down the equations. So there's a solution. It has this form. There's a common gain sequence, which is just a bunch of matrices. I'll write down a form if you want, or maybe not, because why bother? Go to Wikipedia. But you can we will construct basically a sequence of matrices so that the estimates just evolve according to this. All right? And what do you think that is? All right. I heard 2 people, I think, say it. That's the innovations. So that's what I called y tilde before. No, I mean, I called it IT before, I meant to say. Well, so it's y tilde t in the book. So Bruce Huyck calls it y tilde t in the textbook. I'll stick to that. And it's what we called IT. It's exactly innovations. So you take the same dynamics as the original system, and you replace the noise by a gain times the innovations. So that's like sort of like an estimate of the noise, if you like. If you could make that equal to WT plus 1, I guess, WT, then you would have exactly the right model. Yeah, so you can't do that, but that's what's going on. And then it's also equal to, of course we can flip this around. Why would I go from this equation to this equation? So this equation's important because, you're mimicking the description of the system. I've got this white noise that's driving my filter, so it looks just like the original system. All right? You put it in this form for analysis. Because in this form you see that you're modifying the dynamics here to basically stabilize it in a way. So basically you're modifying the state gain here and stabilizing the system in some way. That's what actually happens in practice. And so remember that's why I said no to you. The goal is that, And boundedness, what are you talking about? I want to solve this problem.
You were talking about the expected value for the initial condition, and I was like, does that really even matter?
It matters, because this is initialized with x hat 0 given minus 1 equals x bar 0. If you don't initialize it correctly, all right, in general, it won't work. All right, if you don't generalize it initially, it might blow up. Under conditions, that's not true, but you do need it. Nothing's bounded. All right, so there are conditions, though, in which you're right. Yeah, so you can definitely make that, but you need conditions. So let's look at some just a few remarks. So what would happen if ht is 0? So go through and look at this. So I write k here, t, k, it's time. What would happen? What do you think would happen if h is 0? So study those equations hard. So your observations are white noise. Okay, so we need to get out our equations and go through them and divide and invert or something. You don't need the equations, right? Don't look at the equations. What would happen if you had no observations? What's your best, estimator? So this is white noise, completely orthogonal to x. Yeah, I heard it? What's that? Not the